Welcome to our presentation on Boyle's Law. In this lesson, we'll explore the relationship between pressure and volume in gases, explain it through the kinetic theory, and discuss its real-world applications. Let's dive in. Boyle's law states that for a fixed amount of gas at constant temperature, the volume is inversely proportional to its pressure. This means that as the pressure on the gas increases, its volume decreases and vice versa. Mathematically, this is represented as pressure times volume equals conatant. Here, P is the pressure and V is the volume. This relationship also extends to changes in conditions, where the initial and final states can be compared using P₁V₁ equals P₂V₂ inch. Boyle's law can be represented graphically in two ways. The first graph plots pressure against volume and forms a hyperbolic curve, showing their inverse relationship. The second graph plots pressure against the reciprocal of volume, 1/V, resulting in a straight line passing through the origin. These graphs visually emphasize how pressure and volume are mathematically related. Let's use the kinetic theory of gases to explain Boyle's law. Gases consist of particles in constant random motion. When the volume of a gas is reduced, the particles have less space to move around, leading to more frequent collisions with the container walls. These increased collisions result in higher pressure. Conversely, when the volume is increased, the particles have more space to move, resulting in fewer collisions and lower pressure. Boyle's law has many practical applications. It explains how air enters and exits the lungs during breathing. Inhalation increases lung volume, lowering pressure to draw air in, and exhalation does the reverse. In syringes and pipettes, the principle is used to draw in and expel liquids. Scuba divers rely on Boyle's law to manage pressure changes underwater and avoid decompression sickness. Lastly, aerosol cans operate by releasing pressurized contents when the nozzle is pressed. Let's take a look at some examples. In this example, we have a gas occupying 3.0 cubic decimeters at a pressure of 2.0 atmospheres. The question asks us to calculate the volume of the gas if the pressure is increased to 4.0 atmospheres, assuming the temperature remains constant. To solve this, we use the equation for Boyle's law, which states that the product of the initial pressure and volume is equal to the product of the final pressure and volume. Mathematically, this is written as P1 times V1 equals P2 times V2. Substituting the given values into the equation, we multiply 2.0 atmospheres by 3.0 cubic decimeters, and this equals 4.0 atmospheres multiplied by the final volume. To isolate the final volume, we divide the product of 2.0 and 3.0 by 4.0. This gives us 6.0 divided by 4.0, which equals 1.5 cubic decimeters. Therefore, the final volume of the gas is 1.5 cubic decimeters. In the second example, we are given a gas sample with an initial volume of 500 cubic centimeters at a pressure of 760 millimeters of mercury. The problem asks us to find the new volume if the pressure is reduced to 380 millimeters of mercury, while the temperature remains constant. Again, we apply Boyle's law, which states that the initial pressure multiplied by the initial volume is equal to the final pressure multiplied by the final volume. Substituting the given values, we multiply 760 millimeters of mercury by 500 cubic centimeters, and this equals 380 millimeters of mercury multiplied by the final volume. To find the final volume, we divide the product of 760 and 500 by 380. This calculation gives 380,000 divided by 380, resulting in a final volume of 1,000 cubic centimeters. Therefore, when the pressure is reduced, the new volume of the gas is 1,000 cubic centimeters. To recap, Boyle's law demonstrates the inverse relationship between pressure and volume of a gas at constant temperature. It's graphically represented as a hyperbolic curve for P versus V and a straight line for P versus 1/V. Real-world applications include respiration, medical syringes, scuba diving, and aerosol cans. These concepts underline the law's relevance in daily life and science. Thanks for watching. To deepen your understanding of SI units, explore our comprehensive resources, including revision notes, past questions, gamified quizzes, and workbooks. These tools are designed to help you master the concepts effectively and enjoyably.